All right, the algebraic approach. Now, so to remove the numerical tedium of finding the rates of change that described before, we approach the problem algebraically. So he's going to do the same thing that we've done above, only in this case what he'll do is instead of substituting x squared with a value as we did above with either 1 or 3 or 2, etc., he's just going to say that xp at it's an algebraic k. So at p it is equal to k at this point. So this point right here, I don't know what's wrong with this tool. It's really annoying me. So this point right here is k, whereas this point right here is h. So at xp, at point p, x is equal to k, and then if we choose a further point, xq is equal to k plus h. So this is not h. This is just basically k plus h, like the same number of units. The number of units you've moved is h. So this point is, for example, let's say this point is 5 and this point is 10. So this is basically 5 plus 5 more units, which is h is equal to 5, and you're moving in h units, and this is k plus h. So at xq is equal to h. Now what he's going to do is that he's just going to substitute the values of xp and xq like we did previously also into this equation. Only the points xp and xq are not 1 or 3. They are now k and k plus h. So he's going to first substitute k over here. This will become k square plus h. And then he's going to substitute k plus h whole square plus 3. And this, if you remember, this expression you have to open up algebraically. So he's saying at p, where xp is equal to k, yp becomes, he's just substituted the value of x into the equation. So this is x squared plus 3. So this is x squared plus 3. And then at where this is equal to k plus h, again you substitute that expression into the equation. This is x squared again, x squared plus 3. And when you remember, when you open up algebraically, you're going to get this result. So this is going to be k squared plus 2hk plus 8 squared plus 3. You must remember this formula, a square plus, so a square plus b square plus 2ab. This is that formula being applied over here right now. So now he has his two corresponding values of y. So for x is equal to k, he has his corresponding value of y. For x is equal to k plus h, he has his corresponding value of y again. And these are those values. So these are basically those two values. Now he's going to find the rate of change once again, which is a change in y. Why does this whole thing get highlighted? So this is a change in y, which you will take from here. These two values you just found right now. The change in y over the change in x. And when you solve this algebraic expression, take a pencil and paper and do this yourself, please. You're going to get this, which is 2k plus h. So what he's trying to tell to you is that this equation, x squared plus 3, when you try to solve the gradient for it by taking one value of x and then taking a slightly higher value of x, and then you take the corresponding values of y and you put them into the gradient formula, what you're basically getting is this expression right here. And now he's saying, now we can do something we could not do with the numerical results. We can let the point q slide closer and closer to p along the x-axis, xq, move it near to xp. The result k is fixed. The result as k is fixed is h tends to 0. So basically what he's trying to say is, like, as you move this point h closer and closer to p, the value of k would be fixed. K would be whatever it is. Let's say k over here is 5. The value of k would be 5. But you're moving, so h, if you remember, was a distance. This point is k plus h, but I can't seem to write it because of this annoying tool. But this is k plus h. And h was the number of units that k plus h was away from k. So as I move this closer and closer, so for example, I decrease the units from 5, 4, 3, to 1 to 0 0.75, 0 0.5, 0 0.25. So the value of h, as you see, the distance is tending to 0. However, the value of k is still 5. The value of k is still constant. This is just what he's trying to tell to you over here. So he's saying for the function y0 x squared plus h at the point x is equal to k, when h is equal to 0, the gradient is 2k. So basically he's saying when h becomes 0, the gradient is 2k. Now this is not a very significantly important result, but you'll understand why he's trying to tell this to you right now. But for now it's enough to understand that as you're trying to get the gradient at point x, you will see that when you start moving this particular point from this point closer towards x, you will see this value will tend to 0. However, this value k would remain there. It would remain fixed. So he's trying to tell you basically that as your function, for the function, if the point is xk and the value of h approaches 0, the gradient is equal to 2k. So the gradient is this value, it's 2k. This is a very remarkable result. The rate of change of the function y is equal to x squared plus 3 is directly related to the value of x. So basically what he's trying to say is that the function y is equal to x squared plus 3, its gradient is directly proportional to the value of x. So as the value of x is higher, your gradient will also be higher. And you can forget h for now, because we're supposing that h tends to 0, and the value of your gradient will depend on k or x. It will depend on this value of x. So if x is higher, the value of the gradient of your function would be higher. This is what he's trying to tell to you. Therefore, the gradient at any point of the function can be calculated by substituting the value of x in the function change in y over change in x, which is your formula for m, is equal to 2x. So he's saying, because we found out that when h is equal to 0, this thing becomes 2x. So now he's trying to say, what is the gradient, what is the value of m when x is equal to 1? So let's go back to our graph. So when x is equal to 1, what is the gradient? When x is equal to 2, what is the gradient? When x is equal to 3, what is the gradient? When x is equal to 4, what is the gradient? In all these instances, what he's basically trying to do is that he's substituting the value of x is equal to 1, x is equal to 2, x is equal to 3 into this function 2x. So this is 2, and you substitute the value of 1 here, you get 2 again. Again 2 into, you substitute the value of x, which is equal to 2 over here, you get 4. And then at x is equal to 3, you substitute the value of x over here, you get 6. So he's trying to show to you that when x increases, the gradient also increases. So the problem of finding the rate of change anywhere in the function y is equal to x squared plus 3 is solved once and for all. We can generally say for y is equal to x squared plus 3, the rate of change of the gradient is 2x. So he's saying, so now you know what the gradient is. So remember at the start of this thing, I told you that the gradient is different at each point. It's different here, 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 they're different here, different here. The gradient is not constant at any point. However, now he's arrived to a generic algebraic equation where he says that the gradient is equal to 2x, and when you substitute the value of x, so basically what he's trying to say that m is equal to 2x, the gradient of this line, the algebraic expression of the gradient of this line is 2x, and when you substitute the value of x at x is equal to 1, you can find out the gradient at this point. When you substitute the value of x is equal to 2, you can find out the gradient at this point. When you substitute the value x is equal to 3, you can find out the gradient of the line at this point. So this is all that he's trying to say here. He's saying you found an algebraic expression that basically tells you what the rate of change is, which means the rate of change is 2x, and then you just substitute that particular value of x wherever you want to find the gradient or the point of the line at, and you'll find out the gradient at that particular point. Now he uses the same exercise for a linear function. Now before we go on to this, let me check how much time I'm left with. Alright Lala, we'll do the linear function in the next video.